we want to explain how a physical system can have agency. That is something that is not that hard to understand, right? You build a system that is a controller that was already understood in cybernetics. A controller has some kind of sensor that measures a deviation from the way in which things should be. And then it has an actuator that can direct the way in which things are towards or away from how things should be. And you measure that difference and you make sure that your actuator is moving at the right moment. So you can have a heating element, for instance, that heats up a room if the temperature drops too low and turns off the heating if the temperature goes too high. And in this way, you can have a single, simple controller. And you can introduce more dimensions of control. And you can also nest controllers. So you have something that controls the controller, for instance, the sensitivity to a sensor. And once you get the system to make a model of its environment, so you don't measure just the temperature right now, but you try to make a model of how the temperature is going to be in the future if you perform the following actions, then your heating can become much more efficient. Because you can now anticipate how long it will take for the temperature in the room to change after you turn the heating and so on, and how early you can turn it off again based on the way in which the temperature moves. And maybe you can even figure out by seeing how fast the temperature in the room raises, whether the window is open or not, and thereby do a more fine-grained control, right? And you can get much more efficient. And so as soon as you connect your controller with a model of the future, you get an agent, because you have now a system that can model different trajectories of how events play out in the future. And these trajectories are branching based on your own decisions. And that means that if you integrate the reward over those different trajectories and you make a choice based on that, you now have desires, beliefs, that's your model, and intentions, which are the paths that you have committed yourself to by making certain decisions at some point. And so it's a very natural progression from a simple control system into a system that is an agent. You need to have a motivational system, something that cares about how things in the world should be. You need a general modeling system, which means a computer that can create its own causal model, irrespectively of what's happening around it. So it can model a counterfactual world, a future world, for instance, or can evoke its own memories and so on. And now the question is, how can we build a system that is capable of general learning? What is the right algorithm to build a learning system? And there are many ways in which you can build a learning system. The simplest one is that you can just try to evolve the right set of functions that you want to have to predict the future. But evolution is a very slow, undirected search in all directions. You just randomly can change the elements of your function and hope that the resulting functions are more useful than the previous ones. And you find out by testing them all and then selecting those that are best. And then you change those a little bit until you get to functions that are where you want them to be. And it's a very slow process that if the problem that you're learning is too complicated, often doesn't converge, which means you're never going to get to a useful result in a reasonable amount of time. And the most powerful algorithm that people have discovered to date in order to learn is called stochastic gradient descent. And stochastic gradient descent works by, first of all, representing the problem in a mathematical form that is quite general. And the mathematical form that people are using is called a neural network. A neural network is often compared to biological neurons and said to be inspired by them, but we don't actually seem to be understanding how biological neurons are working if we compare the two. Basically, there's a superficial similarity to a toy model of biological neurons, and that the reason that it works like a biological neuron might be almost accidental. Basically, a neural network is a mathematical model that consists of weighted sums of real numbers that are arranged in chains. We have these, every layer is made of lots of sums of the previous layer, where you sum up the different numbers that come from the previous layer, and you give weights to them, which means you multiply each of these factors that go, or each of these summands that go into the sum. And by changing these weights, by changing the factors by which you multiply the value from the previous layer, you can change the outcome of the function. We also introduce so-called nonlinearities, which are basically a fancy way of saying that sometimes you don't have continuous changes, but you have if-then changes in the network. So you, for instance, a simple way to introduce an if-then change is that you say, if the value is below 0, we just set it to 0. And these nonlinearities allow this model to also express if-then relationships. And it looks like a very clumsy way to that we should represent every thing in the world as weighted sums of real numbers that are chained behind each other. But it turns out that the benefit of doing so is that we can introduce gradual changes into the model. These gradual changes working by changing these weights until the result becomes more similar to what we want to express. And stochastic gradient descent is a way to figure out how to change these weights in very small incremental steps to get the results gradually closer to the function that we want to have. So imagine you have a function that tries to express whether a photograph depicts a cat or a dog. It's obviously a very complicated function. And it first of all works by disassembling the input into a form that the model can understand, which means numbers. So for instance, you can take all the pixels and translate each pixel into 3 color values. Each of them is a number. And then you arrange them based on their position in space. And then you feed this to the map, you feed this into the network. And then you take a few hundred of these layers. And in each layer, you take maybe millions of these units. And you make a very dense connection across the layers. And then on the outcome, you have maybe 2 outputs, and one is it's a cat and it's also a dog. The third one could be we don't know what it is, or it's something third, right? And now we feed it in millions of pictures of cats and dogs, and do statistics over them. And whenever the result is not correct, we have an error in the system. And for that, we basically look backwards through the network and see how much every of the connections contributed to the error. And then we shift every of these connections that contributed to the error a little bit in the right direction. And this looks like it's a very expensive and slow procedure, and indeed it is. But it can run in parallel. We have many, many pictures that we feed in. And then in 2017, a group of people had an idea. They said, instead of doing statistics over everything that happens in the previous layer of the network, let's have a second neural network in every layer that learns what to pay attention to, which part of the statistics we actually need. And this model is called, this approach is called the transformer. It turns out that the transformer is a much more efficient way to train neural networks. And so we could train neural networks on things that we couldn't train them before. Also, what happened in the meantime was the computers got larger and cheaper. So people could use very large data centers to go through very large amounts of data. And when MSF started to work on things like this in the 90s, I was in a lab in New Zealand, and I tried to find grammar in an unknown language, in an unsupervised approach. And the unknown language that I was using was English, because it was unknown to the computer. And it was very easy to get a large set of English documents for me. And I got the largest computer that we had at the department, which had 2 gigabytes of RAM. And I used it as efficiently as I could. So I did in-memory compression with programs that were written in pretty low-level C, and tried to do statistics over the language. And indeed, I discovered grammatical structure. And what I noticed is that the closer I was discovering the structure, just by looking at data compression principles, by how well different words were able to predict other words across sentences, I was also able to get closer to the semantic structure of the text. And I thought if I could do much better statistics, I would find more and more of the semantic structure. And this would enable me to build models that would be able to construct sentences in very much the same way as it was constructed in the original text. But I only worked on this for about a year. And then I abandoned the area almost completely, and only looked at it back when GPT-3 came out. And the GPT-2 was the first time I really noticed these models in more detail. And I realized that they found a way to make this more efficient by finding efficient ways to do the statistics. And this was actually what this transformer was all about. And now we have a way that learns structure and language by predicting the next word, and then encoding the difference, training based on that difference, the violation of the prediction of the next word. And this idea was formulated in neuroscience by Carl Friston, that we learn by predictive coding, that we try to predict how things are going to play out. And whenever something doesn't play out the way we predicted, we change our model. But I think we can also see that GPT-3 And similar transformer models don't learn in the same way as human beings do. They learn much slower, but they're also able to integrate over more data. They discover first this stylistic structure and things like grammar and text, and then at the last thing they discover semantics. And for us, it's the other way around. We first, in some way, learn semantics, what the thing means, and then we learn more niceties like style and syntax. And so we basically have a motivational system that determines relevance for what we interact with. And we have a cybernetic system that controls the behavior of a baby before it has a very sophisticated perceptual model of the world.